Morning, how are you guys? Welcome to this brisk morning in Krakow. Welcome to the 5th annual Digital Dragons. This year we have over 1,000 Polish and foreign participants, about 80 submitted indie games, 90 speakers, so we have plenty to discuss, plenty to see, plenty to learn. All that means that Digital Dragons have become a lasting element of the games sector landscape. By the way, my name is Olaf Orzański. I'm here on the behalf of Krakow Technology Park. And skip the forwards and just go. Let's head to our first speaker. This is my first time, so you know, it can be seen. Mr. Michał Olejnik is a graphic designer, programmer at Plastic. He's responsible for the rendering engineer of Bound, a PS4 exclusive title being developed in collaboration with Sony Santa Monica Studio. Ladies and gentlemen, please welcome Mr. Michał Olejnik.
Hello everybody, can you hear me well? Alright, cool. My name is Michał Olejnik, I'm a graphics programmer at Plastic, and I'm here today to talk to you about the rendering and post-processing effects in our new game Bound. So about us, about Plastic, we are a 9-person development team based in Łódź, and we have demo scene roots which shows in the aesthetic and technical aspects of our products. We are a PlayStation 4 developer, and we are working in close collaboration with Sony Studio Santa Monica, who is our publisher and also aids in some areas of the development. So far we've released 3 titles. The first one is Linger in Shadows, which is how our collaboration with Sony started, and it was a technical demo for the PS3 which showcased the graphical capabilities of the console. It was released in the early life cycle of the console. Then we released a very story-driven game, Datura, also on PS3. And our latest title is the Godzilla Benchmark, which is available on Steam and Godzilla website. So a few words about our new game Bound. It's a PlayStation 4 exclusive title, and it aims to combine classic games and not games. If you don't know what's a not game, well, it's basically something that cannot be truly categorized as a game because it doesn't consist of classic game mechanics, so you can think of it as some kind of interactive experience rather than game. And depending on how you want to play our game, you can tell us that it is a game or not game, so it's up to you how you want to play. And as I said, our titles have very strong demo scene influences, and it shows. As you can see, this is one of screenshots from our game. There is a lot of very abstract, very sharp shapes. So we wanted to make sure that we showcase that as good as we can. We don't have particularly complex shading, but we play a lot with shapes and colors. So we wanted to have a very high resolution artifact-less pipeline. So we are rendering in native 1080p and 4 Msaa samples. What's more, our character is a ballerina, so we have those beautiful motion captured animations from a real-life performer. So we wanted to showcase the fluidity of the movement in ballet. So what we did, we aimed for the 60 Hz display, so there is a lot of firepower needed for those 2 tasks. Also, I have for you some other screenshots. And everything you will see up to the photo mode part of the presentation are in-game screen captures, not altered in any way, and rendered with the rendering settings that you will see in the shipped game. Back to talking points. I would like to start with our rendering pipeline, though this point will be rather brief because our pipeline is very simple by necessity, so I will explain why is it so and give you a general overview of it. The main part of the presentation will focus on the post-processing effects in our game, and of course I will give you a general overview of everything we use, and then I would like to focus on those 3 effects in particular because we have some interesting improvements which I think will interest graphics programmers. So those are screen space ambient occlusion, reflections, and volumetric lighting. And in the end, I would like to touch on the problem of compositing those post effects, because not many titles ship with Msaa rendering. It can be quite problematic bandwidth wise to truly composite this image in an effective way without losing the detail on the edges. And the last part of the presentation, if I only make it in time because I have a lot to cover, is photo mode. I will tell you a few words about our very simple to implement temporal AA solution for photo mode exclusively, give you some tips and tricks how to do this final refinement on your image if your game has a photo mode, and share you a lot of screenshots. So the first part, rendering. Our game was designed with stereo rendering in mind. So what we knew, stable 60 Hz was a must, but we already wanted it. What we also knew, that natively we should render to half 1080p render targets per eye, but when you lack this sub-pixel detail, the image flickers a lot in motion. So we wanted to have some kind of sub-pixel detail, some kind of AA solution. So we tried the 4X Msaa. It helped. Sony, on the other hand, recommends 1.5 times super sampling. And after combining those, it looked really stable in motion. So we ideally would like to do both. So we'll see with what we will ship, but this is our target as far as stereo rendering goes. So of course, we had to balance normal 2D rendering and stereo rendering. And by analyzing the contents of our graphics pipeline, we knew that some of the workload is already eye independent, but still takes some time. For example, one thing that is kind of exclusive for our game is that everything is generated procedurally. Basically, all the content, apart from the shaders, is done by the programmers and procedural generation algorithms. And we use compute shaders for that, so it takes quite a lot of time, 1 to 4 milliseconds. So if you're rendering in 2D, you have 60 milliseconds for entire frame, and in stereo even less. So it already takes a lot of time, depending on the circumstances. We also needed very sharp shadows, because any kind of artifacts really show in our game. So we have as much as 4 shadow cascades, and many other smaller tasks that are eye independent. On the other hand, there are color passes, 2 for stereo, 1 for 2D. So we had to play around there and maximize our workload and figure out what we can do where. So cost already doubles, of course, when you're rendering 2 eyes, so there is enough time for simple forward renderer, and this is basically why our renderer engine has to be very simple. But Bound is still a 2D game. We didn't want the core aesthetic of our game or any kind of content to differ between stereo and 2D. And we, of course, wanted 1080p 4X Msaa 60 Hz rendering in 2D, but we didn't have super sampling. So basically what happens is that we have a lot of time on GPU left when we are doing 2D rendering. So that could be spent on high quality post-processing, so this is exactly what I will be talking about in the latter part of the presentation. So basic forward shading, something that's been around for quite a while. Everything in our game is dynamic, so there is absolutely no way to pre-compute global illumination. When you move, the whole world shifts around you. It reacts to the proximity of the character. I will show you a brief example later. So we can pre-compute GI, and real-time GI algorithms are just ridiculously expensive, so we couldn't afford that. So we have a very old-school rendering pipeline with one sunlight and fill light. And most materials are purely diffuse, Lambertian, so this simple n.l. So there is not a lot of computation going on, but what is most expensive are our shadows. We have 4 2K shadow cascades filtered with expensive PCF 5x5 kernel. So this is percentage closer filtering. And we may ship with 3x3, we'll see. And one particular feature of our game is separate shadow map for the main character. When our main character, the ballerina, dances, there are a lot of procedurally generated content, some kind of, let's say, dancing choreography around her. And if you don't have enough shadow map resolution for it, it really, well, there are really ugly shadows, and it really catches the eye. So we didn't want to do that. And if you're interested in our effects, our dance choreography and other things, I invite you to Andrzej Uszako's presentations tomorrow at 6 p.m. who will be talking about physically based effects in our game. And other thing, which is quite important later, is that we have only partial depth prepass, so depth only rendering to minimize the shading overhead, and some occlusion cooling, but it is adjusted per object type because everything is procedurally generated, so we have to, the programmer who wrote the algorithm knows the best, what is the most efficient way to render it, so he's in charge on figuring out how to do it the best way. And this is basically the most interesting thing about our rendering pipeline because it's very simple, though there are a few static scenes, very little and maybe not quintessential to our game, but we are using some pre-baked lighting for those scenes, and we are using pretty much an industry standard Unreal Engine 4 based shading, so we have popular Torrent Sparrow BRDF for specular lighting, and we use image-based lighting with split zoom approximation for the specular cube maps, just like Unreal Engine 4, and parallax corrected cube maps, so we can achieve those pre-computed local reflections. And of course, with that simple pipeline, if you have big shadowed areas and simple ambient lighting, it really shows how everything flat is. So we had to do some tricks to combat it, but honestly, we didn't have a lot of time for it, so we improvised. What is quite specific to our game is that we have procedural placement of the UVs, because, well, all the content is generated on the compute shaders by the programmer. So what we did is to increase, bend the UVs in the shadowed areas. Basically, during shading, we check out if there is a shadow or not, and we displace the UV. Then that way, we have, well, more detail in the shadowed areas. So it kind of hides this lack of lightning in shadowed areas. Of course, geometry reacts to the proximity of the characters. So if you have a long, flat floor, it just the geometry constantly shifts, so you don't see that it is flat, because it's not. Geometry moves. We also had some other well-known tricks, like clamping adaptive luminance, so our eye adaptation algorithm doesn't adjust a little bit too well to shadowed areas, so they are not too bright. We want to keep shadowed areas quite dark, because if they are not, you can really see the lack of detail. And we also have ambient occlusion for small-scale occlusion, but that will come later. So, post-processing. Very brief overview of our current gen algorithms that we implemented. We basically have HDR rendering as everybody to an RGA render target. Then we use adaptive luminance to adjust the brightness in post based on the average luminance in the current shot. We of course have some quick bloom implementation. This is also something that's been around for quite a while. And we're using very beautiful depth of field with hexagonal blur, which I will showcase you later on the slides with photo mode screens. Of course, we have the algorithm that I mentioned, ambient occlusion, reflections, volumetric lighting, and after all of this, we are using tone mapping to adjust the image to low dynamic range display using ACES curve, and on this low dynamic range buffer, we do the final polishing of the image, so we use if artist desires some kind of color correction with a 3D texture, or vignetting on the edges. So let's focus on those three algorithms in particular. So we have screen space ambient occlusion, and this is algorithm that I think everybody who is a little bit interested in computer graphics knows a lot about. It debuted about 10 years ago with the patch to First Crisis. So basically you estimate the shadowing based on geometrical detail without any kind of information about lighting, and this is what it looks in our game. So the problem in our game was that the ambient occlusion algorithm is very soft by very nature of this phenomena, and softness doesn't fit our game. And we are using scalable ambient obscurance algorithm by McGuire and Mike Msaa, and it was created to specifically combat any kind of occlusion, big, small, medium, but we wanted small only, because if we have a soft lighting, it really shows in our game. So we just use a very small radius, some temporal filter, and it's not perfect aesthetically, but better than completely flat shadowed areas. The one thing that's the most interesting is the compositing of the image. There are some discussions where they are going around all the time whether you should apply ambient occlusion only in shadowed areas or everywhere. For example, Uncharted series uses it only in shadowed areas, whereas The Witcher 3 used it everywhere. We knew that we wanted to do it only in the shadowed areas, and that was a problem, because to compute ambient occlusion, you need a full Z buffer. And we don't have that because we have only a partial depth prepass. So instead of doing it before the shading and compositing during the shading, we could do it in post, output some kind of extra G buffer with a shadowing mask. But we have 1080p render target with 4 Msaa, and going through that memory can be expensive, especially in stereo, as we need this ambient occlusion in stereo as well. So what we came up with was to use ambient occlusion from the previous frame with a little delay. And the first implementation was just a straightforward application, and what happened was that the ambient occlusion was swimming. When you jiggled the camera, you saw it move around. So we used a techniques common within the temporal anti-aliasing solutions. So we compute, during the shading, we compute a motion vector in place to determine where the current pixel was during the previous frame. And then we use this motion vector information to find it in the previous frame ambient occlusion buffer. And the consequences were surprising because there was basically no cost for us. Apparently we are very memory bound on our shaders. And what's more, we can, instead of starting in a position where it would be expensive to add ambient occlusion, we can actually save some time on it because we didn't really have any work on our asynchronous pipelines. So we put it there, and it runs asynchronously during, at the moment, I think, shadow map rendering. Of course, there is some ghosting. When you do reprojection between the frames, some information that was in one frame won't be available in the second one. And I would like to show you the video. I don't know how well you can see, it's rather dark, but basically I'm switching behind our AO and no AO, and this is our ambient occlusion buffer. And what I mentioned earlier, that we have this geometry that reacts to character. Well, as I said, the display is not very well, so keep attention here. Maybe you will notice that the ground around the princess shifts constantly when she's moving. So this is the way we hide the flatness. Can anybody see it? Cool. Okay, I think now I turned it off. So if you don't see it, that is because there is nothing to see. With ambient occlusion turned off, basically you can't see the displacement in the geometry in the shadowed areas. So it's really necessary. Without it, everything falls apart and our game is completely flat. And now example on our sea of cubes that you can see that there aren't really many reprojection artifacts. Everything seems pretty natural. There's no delay, there is no gaps in the ambient occlusion composited with the image. And I will try to catch some ghosting now. And you can probably see even on a very good display because, well, that's the point. But basically when you jiggle camera around back and forth, you can see a little ghosting. There is no ambient occlusion information behind the character from the previous frame, so there is nothing to sample from. And the same thing goes for the screen's edges. But basically, if you're not looking for it, it is not noticeable. At least I don't think anybody of our playtesters ever saw it. So I think it works pretty well. And it's a kind of nice hack when you have very little time for GPU. All right, second algorithm, screen space reflections. This is an example. Sorry. This is an example of screen space reflections in our game. So you can see that the floor reflects the environment. So I have prepared a lot of slides for both screen space reflections and volumetric lighting in case you want to go it by yourself later after you download the slides and analyze how it works. But I would like to show you a demo. So we want to add reflections on the floor. I try to increase the brightness. I don't think it will work that well. So I will maybe just increase brute force the reflection intensity. Can you see the reflections here? All right, cool. So basically everything that was already rendered to the color buffer can be sampled, and we can obtain reflections from the screen space. So basically there is this light switch. So I will show you the ray. We have to ray march. This is basically this ray. So the way it usually works with industry standard solutions is that you run pixel by pixel, you check the collision with the Z buffer, and when you hit this collision, you can sample the color buffer and add the reflection. But as you can see, if this is a 1080p render target, then we have like 600 pixels to ray march here, so it doesn't usually work that way, you just don't have time for it. So what you do is that you increase the step size, so you ray march every couple of pixels. And when you do that, the reflections fall apart. The artifact that you get is this kind of irregular pattern, and it really catches the eye, it's not acceptable. So what you do, you add a per pixel jitter, and that way every pixel starts in different points. So you exchange the artifacts for the noise, and then you try to combat the noise. So that way we have these kind of noisy reflections. And this is not a physical phenomena like in offline rendering, this is just in the error in our approximation, in our raycasting algorithm. So of course you can combat this with, for example, blurring the reflection buffer. Yeah, but by the time you do it, there is still, if you do mirror reflections, a perfect mirror, not glossy reflections, and you do all that I said, then you end up with something that looks like glossy reflections, despite the fact that you started with mirror ones. And obtaining glossy reflections is an industry well-known solution. It debuted with first Killzone, so the first basically big game of current console generation. So you have all those weird little tricks that can give you good-looking glossy reflections. And if you add variable roughness maps and normal maps, then you can't really see this noise, which is fantastic, but literally nothing of it applies to our game. We don't want glossy reflections. Any kind of softness in our game just stands out, doesn't fit the aesthetic. We need a perfect mirror reflections, and we have absolutely no surfaces with variable roughness or normal maps, but often long and flat surfaces. So basically everything that's the enemy of screen space reflections is here. And linear remarching, even if we amp the quality, amp the cost, still has some noise on the object edges. While we don't have much detail on the surfaces alone, so if red gets blurred in red surface during reflection, it's alright, but on the edges there is still noise. So what we needed was screen space reflections that are pixel perfect. And we tried to use an other solution that was briefly described in some literature, but not very well, not very well described. Nobody provided a full source code, so I started to do it from the very beginning. We use a hierarchical Z buffer, high Z, which represents Z buffer as min-max quadri. So basically you map the Z buffer, and each texel stores the minimum and maximum value of depth in the MIP above. And you use that to jump through big amounts of space in screen space. And we use a modified DDA remarching algorithm by the same guys who did the ambient occlusion implementation that we use. And it's extremely arithmetical operations heavy and has a low wave occupancy. So it basically means that it uses a lot of registers. And when you use a lot of registers on the GCN architecture, that means that you fire up less threads. But we have a lot of time for post-processing, and GCN is pretty good with arithmetic operations. Of course, even I can read the code from here. It's more for you if you're interested after the presentation. But this is where our loop starts, and this is where it ends. So there is a lot of ALU ops. Fortunately, most of it is full rate on GCN. There are only 2 float divisions. Everything else is full rate. So there is an example for you to walk later on when you download the presentation if you're interested in our algorithm. But what I would like to do today is to showcase you this in practice. We have a high Z remarching algorithm. I will up the brightness again. And I will drop the resolution so the lines are bigger. and basically we want to ray march this ray. But we are doing it using the algorithm I described. And I have visualization step by step, but I will skip a few first steps because well, they are too small. I want to start at greater level of coarsity. Maybe we'll do with this pixel. So basically what happens during each iteration, you try to traverse the current MIP level of your high Z acceleration structure. What you see on the screen, the blue lines, are the boundaries of the high Z MIP cells at the current level of the algorithm. And what you see here, the red part of the ray, is what we already checked during ray marching, and we know there is no collision. But the green part is where we want to check if there is any collision at all. So the way you do it is that you compute the intersections with the current cell, and those intersections you calculate the depth of the ray in the camera space. So having that, you also have the depths in the current cell. So you can use those depths to check if there is collision or not. And in that case, there isn't. So we can ray match further. As you can see, green line changes to red. That's great. And also the MIP level changes. Essentially, it is because the high Z ray marching algorithm is a greedy algorithm. And that means when we are doing well, then we assume that we'll do better. So if we skip a big amount of space, we want to up the MIP level and try again at a higher level. Of course, this can work either better or less better. But overall, it greatly accelerates the process. So, for example, here is the refinement steps. We are basically approaching our reflection. We are refining what is our intersection point. All right. So, as I said, I prepared all the slides where you don't probably see it, but it is the same thing that you see on the screen before. So basically, if you're interested in how this algorithm works and want to work through it at your own pace, please download the slides later. And screen space reflections demonstration from our game. So you can see example. There are a lot of free spaces where ray marching is quick, and here where ray marching is worse. Here is a heat map, how many iterations of the algorithm you need to execute before you find the reflected pixels. So if you don't have a fragmented Z buffer on the way, then it's basically about 32 steps. Red is 128, so cyan is 32, and when you have more complex structures, then it takes a lot of time. And now I will show you that in motion. So at the moment, in this very scene that you see, there is a half resolution buffer for reflections, and it takes about 1.5 milliseconds on the PS4. So it's not cheap, but we had some free time for post-processing in 2D, and this is something that we don't use in stereo. So ultimately, I think it was worth it, and it works much better in our case than linear ray marching. Although I think that our game is one of the few that will really benefit from it, because we just couldn't do anything with any other algorithm. So volumetric lighting, this is an example from our game. I will show you a video later. We are using a very popular and elegant algorithm by Bart Wroński. Basically volumetric lighting, volumetric fog, light shafts, however you want to call it. So the way this works in offline rendering is that you shoot a ray from the camera to the pixel, and you ray march through it at some discrete steps, and you check if there is any light that's scattered towards you or outside of the ray. So if there is any absorption on the way to the pixel, you just want to which lighting you want to compute. And the way this algorithm works is that we use a very coarse volume 3D texture to approximate those rays. And data is divided into frustum aligned voxels. So they are not really voxels because not all of their edges are perpendicular, and they've been given recently a very cute name of froxels, and this is what we use in our algorithm. So basically, for each frog cells, we take the center of it. We see in the shadow map if there is any kind of shadow or if it is lit. We add this information, and then in the second pass, we ray march through the Z indices of the 3D texture to accumulate the scattering and absorption. And during composite pass, we use pixel coordinates and the buffer to figure out which place in the 3D texture we want to sample. And our game uses homogeneous medium, so that basically means that fog characteristics don't change in in space. They are constant in the whole game world, which greatly simplifies calculations. And we don't have any punctual light sources, so we only use the sunlight shadow cascades. So time for the demo. This is a completely exaggerated example. I don't think I did it. If I exaggerated well enough for this display, but hopefully you can see how it works. So, I prepared a test case. We have a scene like this. This is taken from one of our levels, and we want to achieve something like this. The real trick about this algorithm is that you have to use very good filtering techniques, because the volume is very coarse, and if you don't use any filtering, there is an absolute mess. So this is what it looks like with point filtering. So basically, if you are using a 3D texture, you have to decrease the normal. If you have a 1080p buffer, yeah, that takes about a couple megabytes, and you don't want to go with your texture memory above that, because memory access is extremely expensive. So you have to take, if you have a 3D texture, you have to take from those XY axes and add to the Z axis. So the resolution that we use is exactly what you see here. So basically, in screen space, for every couple of pixels, there will be the same frog cell that is sampled during the composite pass. And obviously, this is stupid because we have hardware support for linear filtering of any kind of textures. So if we add it, you don't see this pixelated noise, but there is still some noise. And the trick that comes with volumetric lighting is that the phenomena that it describes, the actual what happens in nature, is very soft in nature. So if there is some kind of lag, when you see that algorithm lags a little bit, you don't notice it as a real artifact. You don't know that it's the fault in the implementation. You think that occurs naturally. And honestly, most of the things in a good implemented volumetric lighting algorithm look like this. Any kind of artifact looks natural. So to leverage that, we can use temporal filtering. So basically, at each frame, we jitter the position of the frog cell for which we evaluate the lighting. And then we accumulate those changes from neighboring frames. So frame by frame, the image quality improves. So what I do is that I jitter first the frog cell positions along the Z-axis, so back and forth. And this already does a very good job. A lot of artifacts disappear. Of course, you can also jitter it around XY axis. And that it helps a little bit, especially with staircase artifacts on the light shafts. As light shafts approach the diagonal, you can see that these staircase artifacts are actually quite severe, and there are some cases in our game where it really hurt us. So if I exaggerate the example, you can see how there are some staircase artifacts here. And what the author of the algorithm suggested is to convert your shadow maps into something that provides a little less detail. So there is so we have no noise from sampling, for example, exponential shadow maps, but it's an extra step that, as it turns out, we don't actually need. What you can do is do some kind of better filtering algorithm. And if you are a graphics programmer, you probably touch upon that subject either at your own time or at your university. So I will give you an example of how this filtering works. So we have a texture, 32 by 16, and each color is a single pixel. And we use hardware linear filtering, so what is provided basically by any GPUs on the earth at the moment. And it looks like this. So the colors are blended with themselves, and they are nicer, but there are still artifacts. So this is exactly the difference that I showed on volumetric lighting in the beginning. And you see some bending issues here, but this is because of the display. It looks nicely on my monitor. What's the worst are those crosses here when the texels meet. So this is exactly what causes those staircase artifacts. And what linear filtering, of course, does is that it takes 2 samples in each dimensions, but you can use cubic filtering, which uses 4 samples to calculate the final color. So if you use it, it looks something like this. Again, these are binding artifacts caused by the display. This doesn't occur on my monitor. And you can think that it is a little bit too blurry, but in practice it works pretty well. So when you go back to linear, you can see that there are some staircase artifacts. And I don't want to cover it a little bit too much, but basically when you do linear sampling, you have 2 samples in 1 dimension, 4 samples in 2 dimensions, 8 samples in 3 dimensions, and when you do bicubic sampling, you have 4 samples, 16 samples, 64 samples, and you don't have hardware acceleration for it. So my first brute force implementation with Msaa per sample composition took about 10 milliseconds on the PS4. I thought that I was going nowhere, but what it turns out, you don't have to do cubic sampling in all the axes. You can use normal linear sampling in the Z axis and on cubic sampling on the XY axis. And there are some techniques that leverage hardware linear filtering. Here is an example if you walk through it yourself. And basically, of course you can't read the code, but basically what it boils down to is there is only 4 samples with a linear sample throughout the 3D texture. So it's an amazing difference compared to what I started with, but it's still quite expensive, especially if you do per sample image composition within an Msaa pipeline. So I encourage you to check up on the sources later, and I will show you a video right now. And of course you probably can't see anything, maybe a little bit of light shafts. So I will encourage you to download the slides later and see for yourself. And final point of my post-processing talk, image compositing. So a big problem. Msaa rendering is usually very effective during simple forward rendering because you shade only once per pixel instead of per sample. But then you have to apply some post effects on this image, and basically you have 4 possible color samples per each pixel. So you can either composite the image after the Msaa resolve or before per sample. If you do it after, you lose the detail on the edges that you worked so hard for with your Msaa rendering. And for some effects it is less severe, for some more. For example, for volumetric lighting, where you have a very high contrast light shaft passing from behind a very dark object, then you see that there is completely no anti-aliasing, that you lose this anti-aliasing on the edge. So it really sucks for our game. We didn't want to do that, and we have to figure out a way to do per sample composition. But it's extremely expensive because if you run per sample composition, you basically quadruple the execution time. Fortunately, there are some tricks that you can use on the PS4. They are not actually available at Windows at the moment. Maybe in the newer APIs, but I haven't really checked that. So basically what you have on PlayStation 4, or what the GCN architecture provides, is an extra texture called fmask, which basically is an integer texture where on each bits there is a compressed information about pointers to colors. So you can basically analyze each sample from a compressed texture, each pixel from a compressed texture, to check out how many samples do you really need to process. So basically, if you aren't processing a pixel that was a triangle edge that was on some kind of middle of the triangle, then you only need to process one sample, which really fixes the bandwidth issues. And there was a problem with doing this with Pixel Shader, and even so my problematic implementation didn't seem to give any difference in performance. So I figured out that I can do it on compute shaders. And this is not possible on DirectX 11, but GNM, the graphics API for the PS4, allows for two things that solve the whole problem, which is basically unordered access views to Msaa textures. If you don't know what's an UAV, it's basically kind of a render target that you use in compute shaders. And you can also read from this UAV and you can read any texture format. In D3D11, I think you can read only R32 floats or something like that. There are very limited options, and we have, for example, RGB816 for the volumetric lighting. So having all these tools, you can use shaders for compositing. Each thread analyzes one pixels, it iterates through the unique color samples, reads from the UAV representing the color buffer, does the composition, and writes back. And here is my test case. Here is a heat map of unique sample colors. So basically blue is one sample, and any middle of the triangle has one sample. Most edges have two samples, so so a green color, and some very high density meshes, like here, have 3 or 4 samples per pixel. So these are some timings. If you do per sample composition, you basically quadruple the time, so this is not a surprise. But what was really surprising, that you can really amortize the cost of my bicubic volumetrics, which is great because they are much better than the standard trilinear implementation. But we can do better. An old approach, but I think it's absolutely necessary if you want to save this GPU time, and it is to write Uber shaders for your compositing. So basically you write a very long shader that has all the post-effects compositing algorithm in it. You wrap those specific algorithms in the preprocessor definitions, you compile all possible permutations, and then you choose and run at runtime what you want to do, which instance of the shader you want to use. So very similarly, each thread uses the fmask, so it can know which color samples are unique to minimize the bandwidth, and then does compositing, averages the example, and outputs the resolved Msaa buffer. So if you do it in one pass, you save a lot of time. Of course, you have to pay attention to the register pressure explosion. Basically, if you add those passes that are in a loop, you increase the number of registers that you use, which leaves you with less threads on the GPU available. And technically, it might be sometimes better if you have a lot of post effects to leave some of those post effects outside of the Uber shader and do normal compositing, though. Personally, it's just a theory because I haven't reached that point yet. And what I can also advise, that if you force unroll your loops for compositing, you probably shouldn't do that, because sometimes a simple loop in a shader is quicker when there are a lot of instructions in the loop. So here are my timings, and what interests me the most, because we never have screen space reflections and volumetric lighting turned on at the moment at the same time, is the worst case scenario, which is 1.30 milliseconds. compared to almost double that before. So it works pretty well and it really saves us. It really allows us to do those more complicated algorithms in our 2D rendering. Of course, there are some problems to consider when you apply everything at the same time, because there might be some dependencies between the post effects. So the most obvious one is that any kind of post-processing effects won't affect your calculation of the average luminance. So this is important for volumetric lighting, which greatly changes the brightness, perceived brightness in the scene. Also, if you are using depth of field and you apply that, then you lose everything, any other post effects on the areas that are blurred. So what we do is basically disable Uber composite during the cutscenes when we use depth of field and in our photo mode. And of course, you have to remember to apply volumetric transmittance after lighting effect. So when you use your fog data to dim the pixel color, you have to remember to, for example, apply the reflections beforehand. Otherwise, it will look out of place. And the shortest part of my presentation, basically a couple words, our photo mode. So we are rendering in 60 Hz, which is great because photo mode doesn't need 60 Hz. It's only available in 2D. So we cap it at 30 Hz and basically use the spare time to brute force fix any kind of artifacts that we have. So extra shadow cascades, we turn off shadow map stability algorithms because they reduce the effective resolution. And when you stop moving the camera and you want to take a screenshot, you don't care about temporal stability. We also up the texture sizes of all kinds of post-processing effects. And we turn off Uber composite, as I said before. And of course, we turn off some performance hacks that are present in the game. For example, we turn on depth right on our raindrops because we don't want depth right on raindrops because it fragments the Z buffer and slows down the screen space reflections when we are using high Z algorithm. But we want them to write to the Z buffer in the photo mode, so the depth of field algorithm will blur them with a correct radius. So screenshots on PS4 are taken with the share button, so there is no point in rendering some kind 16K textures because it will never be captured. So instead of playing around with your texture sizes, checking out if you have enough memory, you can use temporal supersampling. So basically you postpone this supersampling algorithm and split it through few frames. And you turn it on only when player stops moving the camera, and then it just does this final refining pass on the image. And if you want to see an example, right now you can play Drive Club, which does exactly that, and other even more sophisticated things like motion blur that way. And what's great about it is that the implementation is trivial. We couldn't really do temporal AA in our normal renderer because we have tons of procedurally generated content, and if we wanted to add temporal anti-aliasing to them, we would have to add motion vector calculations for all those content. So I would basically have to take my whole team of programmers and tell them, okay, for this month we are only writing motion vectors, and even then we don't know if it would be good enough because we already have Msaa. So we kind of scrambled it, but in photo mode, when player stops moving the camera, the implementation is trivial. You don't have to do anything apart from jittering your projection matrices and blending the color buffer. There are no motion vectors and no rejection factors needed. So we want to temporal filter everything. We jitter the projection matrix by sub-pixel offsets. We also do it for shadow projections, and I will show you examples why. And what you should also remember is to use negative MIP bias for your textures, because if you do amortized supersampling, then the derivatives which are used for UVs to choose the correct MIP level are, well, incorrect. You have to accommodate for that with some external bias factor. And what we do, but I don't know if it is the best way, but it's extremely simple, and it works for us, so I did it anyway. So I turned off the blur and temporal filters on all my post effects, but I kept the jitter. And I use the final temporal filter pass on the low dynamic range buffer to get rid of that jittering artifacts, and it works pretty well. So here is an example. I don't think that you can really see that much because the details are very minor. So here is a zoom. Basically, the best thing is that jittering those shadow projection matrices completely loses the staircase artifacts on the shadows, which even with our high resolution shadows are quite visible. And it also reduces shadow acne, which is great because if you have a photo mode, you probably allow the user to change the field of view a lot. And when you change the field of view, your normal bias settings that are used to remove the shadow acne are no longer up to date. So even if you set a couple exemplary shadow biases for different field of views, it's still nice to have this final pass that fixes those artifacts. And of course, like any kind of temporal algorithm, it brings out the detail that is sub-pixels. For example, a shadow thinner than a pixel or a very thin objects. It also works great to compensate for the lack of anisotropic filtering. If you are using custom PCAF resolve for your shadows, you don't have anisotropic filtering. So it really fixes those kind of artifacts, and in the same way it fixes surfaces at oblique viewing angles. So this basically all, some photo mode goodies for all, but I'm not sure how well you can see that. You can see our hexagonal blur in action. So I'll just keep jumping through the screens, and what I wanted to do with the presentation is to put it on the Twitter a couple weeks later when I can add some stuff that I kinda smuggled on the slides, but I wasn't to well, give it a proper name. So the presentation is correct in nature. Some of you probably know what I'm talking about because I wrote on that before. And if you really want the presentation right now, you can just email me. You can email me and I will send you what I have right now. You can see some of our depth of field algorithms in action. Thank you very much. Jest czas na pytania? So sorry everybody, we don't have time for questions. So if you want to ask me anything, please feel free to approach me.